In today's video, we're going to start a series on electrochemistry. Electrochemistry is just chemistry. It's redox reactions, really. And the difference is that now we're looking at something that's pretty applicable to everyday life. You can either take a reaction that's spontaneous and get energy out of it that we can use as electrical energy, or you can input electrical energy into a reaction and force a redox reaction to go that may not otherwise be spontaneous. So the only new stuff that we're really going to be learning here that we haven't seen before is just some information about how we interact between electricity and chemistry, and then how does the spontaneity stuff from the last series of videos fit in to redox reactions that we see in electrochemistry. Electrolysis is a chemical reaction, a redox reaction, that's forced to occur when electricity is passed through a liquid conduction medium. Electrolysis happens in something that we call an electrolytic cell. Electrolytic cell has to have three features. One is there has to be a source of electrical current from outside. So electrical current comes in to the cell from an external source, like a battery, for example. There has to be a conducting medium. Now this could be two things. One kind of a conducting medium could be a molten salt. So something like sodium chloride. If you get it hot enough, it'll turn into a liquid, and then the particles are free to move. So it has to be able to conduct. That makes it a conducting medium once it's melted. Or you could also have an electrolyte that's dissolved in water, because electrolytes conduct electricity. You'll have positively and negatively charged ions that are mobile because they're free in an aqueous solution. And then you also have to have electrodes. There are two electrodes. One electrode is called the anode, and the anode is where oxidation occurs. And the cathode is the electrode where reduction occurs. And the connections between the outside electrical current and the inside chemistry, the conducting medium, is the electrodes. These electrodes are sticking into the conduction medium, but they're also connected to the electrical circuit. The cell reaction is the overall redox reaction that's taking place inside that cell during electrolysis. For example, say we were going to melt some KCl and pass electricity through it. At the anode, we would see anions being oxidized. Well, the anions in KCl are Cl minuses. They would produce Cl2s and release 2 electrons. That's what the balanced half reaction looks like. But if you originally had K pluses and Cl minuses, as these Cl minuses get reduced, we're going to have a positive charge buildup at the anode. Nature hates that charge imbalance, and so anions, other Cl minuses from other places in the electrolytic cell, are going to migrate toward the anode to balance charge. At the cathode, you're going to have the opposite thing occur. Cations are going to be reduced. In KCl, our cation is K+. So that'll collect an electron and be reduced to potassium. But the Cl minuses near the cathode are still there, and so we get a negative charge buildup because of a bunch of Cl minuses. So other cations, other K pluses from other places in the cell, will have to migrate towards the anode to make up for the fact that the Cl minuses are now making an unbalanced negative charge. Let's take a look at this visually. Here is our anode right here, at which oxidation is going to take place. So what we're going to see is Cl minuses being oxidized to chlorine gas. So what's happened after some time elapses is that we now have a bunch of Cl2s here. All of these things are representing Cl2s. But the Cl minuses that got oxidized aren't there anymore. So in the local region around the anode, we have an abundance of positive charge because of all the K pluses that are still there. So chlorines are going to have to migrate into that zone to make up for the fact that the charge is imbalanced. And so that's what we see happening at the anode. At the cathode, we have pretty much at the beginning a balance of K pluses and Cl minuses. But these Ks are going to reduce, and they're going to form a pool of liquid potassium down at the bottom as K pluses collect electrons that are coming down into the cathode from the external current source and then use that to reduce down to K. So we've seen this puddle of liquid potassium develop down here, but in the region around the cathode, we now have only minuses, whole bunch of Cl minuses, but the K pluses have all been reduced. So because there's a big negative charge imbalance here, the potassium ions are going to migrate from the other parts of the cell towards the cathode to balance the charge. Of course, this flow keeps going in both directions, and if you look at the big picture, this movement of ions is going to complete an electrical circuit. So what we see happening here is Cl minuses are migrating toward the anode as the Cl2s get formed by oxidation and leave a positive region. The K pluses are moving towards the cathode as K pluses that were there at the cathode become reduced and leave a negative charge buildup. At the anode, this reaction is occurring. Cl minuses are becoming Cl2 and they're giving up electrons. Those electrons then flow in the direction of the positive charge of the current source, a battery here, because electrons are attracted to positive. Electrons are repelled from negative, so the electrons coming off of the negative terminal of the battery go into the cathode, and that's what causes the K plus to reduce to potassium. So we see negative charge going in this direction around the circuit, and in the case of the potassium ions, we see positive charge going the other direction around the circuit. The electrolytes, their ability to move in here, completes the circuit, and so we have this flow of electrons around and around and around in the circuit. That's forced by the battery, and it causes this chemical reaction to occur in the electrolysis. Now, if you had something spontaneous happening in here, you might be able to force electrical flow in some direction or another and get some energy out of it. In a later video, we'll explore that possibility. Now, in this example that we just looked at, it's clear what's going to reduce at the cathode. There's only one thing that can, and that's the K pluses. They'll collect an electron that's coming down the wire and reduce to potassium. At the anode side, it's clear what's going to oxidize. There's only one thing that can there, too. That's the Cl minus. Two of them will reduce to a Cl2 and give up two electrons that then go down the wire. Now, if this KCl was not molten, but was instead dissolved in water, this would not be as clear. And here's why. In aqueous solution, in addition to the ions that are dissolved in the water itself may also be oxidized or reduced. For example, the reduction of water happening at the cathode would be when two water molecules collect two electrons and form H2 and two hydroxide ions. That's a cathode reaction. And at the anode, oxidation can occur for water. And again, it's two water molecules, and the oxidation here is O2 gets produced. And then byproducts, 4H plus and 4 electrons. So for that reason, you need to decide what's really going to happen. Is it going to be water, or is it going to be the other species that gets oxidized or reduced? For example, in the electrolysis of KNO3, you have two competing cathode reactions. One of them that we've already seen in the last example would be potassium ions reducing to metallic potassium. But also at the cathode, we could see water reducing to H2 and yielding two OH minuses, which is going to happen. At the anode, there really isn't a competing reaction for water. NO3 is not something that's very likely to oxidize. In fact, in general, oxyanions don't oxidize really well. They typically will reduce. So the only thing at the anode that can happen, the only oxidation, is the oxidation of water in an aqueous solution. So O2 is formed, 4H pluses, and 4 electrons. That's the oxidation reaction. That's what happens at the anode. The reduction is also water. That's the reaction that's preferred when the choice is between potassium reducing and water reducing. So the water gains 2 electrons, makes hydrogen and 2 OH minus. That's the reduction that happens at the cathode. If we sum these reactions together, in order to make the electrons match, we have to multiply the second equation by 2, and we end up with 6H2O on the left, and on the right we end up with an O2, 4H pluses, 2 H2s, and 4 OH minuses. But we know that H plus and OH minus don't exist in solution to any great extent, so that's really going to make 4H2O. So if we take 4H2O from both sides, we end up with 2H2O on the left, and that gives us this overall reaction. 2H2O decomposes to O2 and 2H2. And that's what you'd expect for a decomposition of water. However, if you do this without the KNO3 present, just put pure water and try and pass electricity through it, this reaction will not occur. So those electrolytes do something. They're necessary. Here's why they have to be there. You can't conduct electricity through water because there aren't any free ions to carry the charge. So if water is electrolyzed, an electrolyte still has to be present for conductivity. For example, in the reaction that we just looked at, where potassium nitrate solution is being electrolyzed, what will happen is, as the water oxidizes at the anode to give O2s, it also gives H pluses. Those H pluses collect around the anode, and you end up with a net positive charge near this anode. Because of that charge imbalance, the nitrate ions have to move in here to balance all those increasing positives with some negatives. At the cathode, the water has been reducing to hydrogen. But as it reduced to hydrogen, it also produced OH minus. So that causes a local negative charge buildup around the cathode. So potassium ions are now going to migrate towards the cathode to balance that charge. And this movement of positives in the clockwise direction and negatives in the counterclockwise direction in this particular circuit keeps the circuit going. If those anions were not in there, you'd have an open circuit in the chemistry part of this reaction, and no electricity would flow through the wire. So how can we predict what's going to happen if you have electrolysis of an aqueous solution? Well, we have a couple of general rules. Here's a general rule for cations. Transition metals will reduce preferentially to water in an aqueous solution. So if you have copper 2, for example, or aluminum 3 plus ions, those species will reduce in the presence of water. The representative metals, so something like Na plus or Ca2 plus, will not reduce, and they will instead defer to water. So by looking at the cation, you can quickly tell if you're going to have reduction of that cation or reduction of water. There are also general rules for the anions. The lower halides, it turns out, will oxidize preferentially to water. So we're talking about Cl minus, Br minus, and I minus. Any other anions will defer to water. In other words, you'll have water oxidizing instead of the anion. Let's apply this to some real solutions. Let's take a look at CuBr2. First of all, let's analyze what's going to happen with the cation. The cation is Cu2+. This is a transition metal cation, so that means it is going to reduce preferentially to water. So rather than water reducing, we will have copper reduce from Cu2+ to metallic copper. The anion here is Br minus. That's a lower halide. So Br minus is going to oxidize to produce Br2. To balance it, you need 2 Br minuses and you release 2 electrons. Let's look at the electrolysis of a copper 2 nitrate solution. Our cation is copper 2, and we saw in the last example that that will reduce to copper preferentially to water. Our anion is nitrate, NO3 1-. Nitrate is not a lower halide, so it's not going to oxidize. Instead, water will oxidize. So we get H2O oxidizing to oxygen, and that gives 4 electrons and 4 H plus ions. Let's look at the electrolysis of a KBr solution. Our cation is potassium, K+. That's a representative. That's not a transition metal, and so it's not going to reduce at the cathode. Instead, we'll have water reducing to make H2 and producing OH-. The anion is Br-. That's a lower halide, so it will oxidize to Br2 and give up those 2 electrons. Well, electrolysis reactions are chemical reactions, and so like all chemical reactions, they operate on the basis of individual atoms, which can be scaled up to moles. And so stoichiometry is going to be an important part of understanding and predicting what's going to happen in an electrolysis reaction, just like it is in any other kind of chemistry. The difference here is that we now have to deal with the outside of the chemical system and start to make a connection with the electrical current part of the circuit. So we need some electrical terminology. The first piece of terminology we're going to use here is the coulomb. Coulomb is abbreviated capital C, and it's the standard fundamental unit of electrical charge. Now, if you've ever rubbed your hair on a balloon and stuck it to the wall or stuck it to the ceiling, what you've done is you've transferred a bunch of electrical charge to that balloon. If someone wanted to quantify how charged up you got that balloon, what they would measure that with is a coulomb. What we need is a way to relate coulombs, the quantity of charge, to something involved in chemistry. And here's the connection. Electrons are charged, and so a certain number of electrons should carry a certain amount of charge. There's a constant named after Michael Faraday, Faraday's constant. Its symbol is this funny script F-looking thing. And here's the constant. It's a ratio, really. 96,500 coulombs is the charge on 1 mole of electrons. So that ratio can be used to solve all kinds of problems, converting from a chemical measurement to an electrical measurement. Another important electrical term that we need to establish is an ampere. Most people will just say amp for short. You may have heard an electrician or somebody saying the word amp. An ampere, abbreviated capital A, is the standard fundamental unit of electrical current. Now, current is the rate of charge flow past a given point. An ampere is defined as 1 coulomb of charge passing by a given point in a circuit per second. So we could define this mathematically. 1 ampere is 1 coulomb per second. Another way that this is useful is to rearrange this equation and recognize that a coulomb is the same as an amp second. An amp of current for a second passes a coulomb. Well, the electrons, you may have noticed in these half reactions, have coefficients on them. So that means moles of electrons are related to the moles of everything else in the equation. And moles of electrons are related to coulombs. And coulombs are related to the current in amps and the time in seconds. So if we can measure time and measure current, we can make some predictions and calculate how many moles of different species are produced or consumed in an electrolysis reaction. Here's an example. How many minutes will it take for a current of 10 amps to deposit 3 grams of gold from a solution of gold 3 chloride? Well, this is the reduction that you'd see in this reaction. We have gold 3. It would gain 3 electrons to become Au. It's a transition metal, and so that's what would happen at the cathode. Now, starting out with our known quantity of 3 grams of gold, what we want to do is turn this into time, minutes in particular. Let's look at the relationships that might help us do that. First of all, I have to convert my grams of gold into moles, and so I'll use molar mass. It's 196.97 grams of gold per mole. So now I have moles of gold. I want to get to electrical terms here, and so I'll use a mole ratio. 1 mole of gold is reduced every time 3 moles of electrons pass through the circuit. So now I've changed from moles of gold to moles of electrons. Now to get this in terms of current, I need to use charge. So here comes Faraday's constant. There are 96,500 coulombs for every mole of electrons. Moles of electrons are now converted to coulombs. Now remember, an amp is a coulomb per second. 1 amp is 1 coulomb per second. So 10 amps would be 10 coulombs per second. So I can use that here. 10.0 coulombs per second could be multiplied by coulombs to give me seconds. And then to finish this equation off, well, I know there are 60 seconds in a minute. So my calculation is done here. When I do all the work, I get 7.34 minutes was how long it would take. In the end here, I'm going to quickly go through some examples of applications of electrolysis that occur in the real world. One of them is called electroplating. Electroplating is the process of applying a thin coating of one metal on another through electrolysis. And by thin, I mean really thin. Many times you can specify the thickness of the coating by using the unit of angstroms. angstrom is 10 to the minus 10th meters, so that's a very thin coat. Here's how electroplating works, and I'll explain this by using the example of plating chromium on a steel bumper. What you do is first make a salt that contains solutions of the coating metal. So in this case that would be chromium. So you make a solution that has chromium 3+ ions in it. And then you immerse a bar of chromium, the coating metal, into the solution and make it the anode by hooking it up to the positive terminal of your current source. Now that's going to draw electrons away from the chromium bar and make it the anode, because oxidation is going to occur there. Now the object that you want to coat with chromium, the bumper in this case, would be inserted into the solution, so that's right here. And this is made of steel, but we hook it up by wire to the negative terminal of the current source. So electrons are going to flow into it. The current source then forces oxidation to occur at the chromium bar, and more chromium 3 ions are created and put into solution. At the same time, chromium 3s are reduced to pure chromium at the cathode, and a layer of chromium gets put onto the bumper. So as time goes by, the chromium bar is going to get thinner and thinner and thinner, and the bumper is going to get thicker and thicker and thicker until you have the coating that you want, and then you just shut off the current. Another example is the production of aluminum. Aluminum, it turns out, used to be very expensive. In fact, historians believe that the crowns that kings wore in the Middle Ages were actually what we would recognize as something like aluminum foil, because aluminum was so rare and precious in those days. But then somebody figured out a way to produce aluminum by using electrolysis, and aluminum has become much more readily available. So looking at this setup here, you can see what they're doing. The first thing that happens is they take molten cryolite. This is this mineral, Na3AlF6, and they dissolve aluminum oxide in it. And so the aluminum becomes Al3 pluses and O2 minuses. And then they pass current through it. So you have an anode, that's these 3 bars down here. These are hooked up to the positive charge. So these are positively charged. And so that's going to cause an oxidation to take place. And that oxidation is O2 minus becoming oxygen. But the real point of this is to make aluminum. And what happens there is the outside of this tank, that whole outside of the tank is hooked up to the negative circuit. So this is negative all the way around the outside. And then what happens there is the Al3 pluses are going to be reduced, because that's the cathode, and make aluminum. Well, that aluminum is more dense than the mixture, and so it sinks to the bottom, and you end up with a whole bunch of aluminum down here in the liquid state. When you have enough of it, you just open the plug, let it all drain out, and then it freezes, and you have solid aluminum, which you can then make things out of. Another application is the production of magnesium, starting with seawater. Seawater is a pretty good source of magnesium ions, Mg2 pluses. If you put it in a basic solution, like a sodium hydroxide solution or something like that, you'll get magnesium hydroxide to precipitate out, and you can get the magnesium then out of the seawater. But it still isn't magnesium. You can't use it. It's an ionic form. So the next thing you do is take that magnesium hydroxide, which is insoluble, but it's a base, and react it with a strong acid, like HCl. And that'll neutralize it, giving you magnesium chloride and water. Now, magnesium chloride is something that you can collect as a solid and melt. So then you melt the MgCl2, and you will have Mg2 plus ions, and you'll have Cl minus ions. You can reduce the Mg2 plus at the cathode and make magnesium, collect it, and then use it to make things. And the Cl minus will oxidize to Cl2 at the anode. And you can collect the Cl2 and use it for things as well, like bleaching or sterilizing swimming pools. Here's another example, the production of sodium. Sodium chloride and calcium chloride are put together in the same mixture in this particular arrangement. Calcium chloride will reduce the melting point, so all this orange stuff in here in this tank is this mixture of melted sodium chloride and calcium chloride. In the middle there's like a chimney almost, and around that chimney is a ring of metal or maybe it could be carbon, that's connected to the negative terminal of a current source. So all the way around here we have this ring, and that current source turns that metal bar, turns that metal ring into a cathode. So at the cathode, the sodium reduces and produces liquid sodium. Now the liquid sodium is less dense than the mixture of sodium chloride and calcium chloride, so it floats to the top actually, collects in this little housing, and goes out a pipe, and then you collect it, freeze it, and do whatever you do with sodium. In the middle of the little chimney is an anode, a little bar that's hooked to the positive terminal of the current source. And so the oxidation of Cl- takes place to produce chlorine gas, which goes up the pipe, and then you can collect that and sell it as well. Here's a really interesting application, refining copper. When copper is first made from ore, it's fairly impure. It's got a lot of iron and zinc, platinum and silver and gold are actually in this copper. And unless the copper is very, very pure, it doesn't work quite as well as copper that's even slightly impure. It doesn't conduct electricity as well, doesn't do the things we most value copper for as well if it's not purified. So here's how they do it. They take a thin strip of copper that's already been purified. So this is going to be pure copper, Cu, a bar of it. Not very much, just enough to get this thing started. And they make that the cathode by hooking it up to the negative terminal of the current source. They hook the positive terminal of the current source up to a large bar of the impure copper that they've just made. Now, they start the current source going, and that oxidizes copper, it oxidizes zinc, and it oxidizes iron, so that they all come off of that bar. However, they don't make the current source strong enough to oxidize platinum, gold, and silver. So those metals stay in their metallic form, don't ionize, and they just sort of fall off of the bar and collect at the bottom of the tank. Meanwhile, they have the current source set so it's just strong enough to reduce copper from copper to pure copper, and the zinc and the iron stay dissolved in the mixture. So as time goes on, the impure copper bar gets thinner and thinner, and the pure copper bar gets thicker and thicker. So what you've done is you've taken the copper, oxidized it to copper 2, and then taken those individual atoms and plated them on to this pure copper bar and turned them back into Cu. So you get a thick pure copper bar. The impure copper basically disappears. And this is something that's really interesting. This sludge that's laying in the bottom of the tank is platinum, gold, and silver. And you can collect that sludge and sell it for enough money to pay for the whole process of refining the copper. Pretty clever. Well, what we've been looking at today in this video are reactions that are forced to happen by an outside current source. You can imagine that if you could get a spontaneous reaction to happen, you might be able to use the chemistry to force an external current source. That's called a galvanic cell, but the common name for it is a battery. We'll talk about that next time.